Okay, so now that we know a little bit about potential energy, and we already know something about kinetic energy, I'd like to spend some time talking about energy conservation. Energy conservation. Conservation laws are a big deal in physics. There are a bunch of them, and they end up being really important. Let's just say conservation, singular. And this is conservation of energy. Now, conservation of energy is it's a bigger topic than what we're going to deal with. We're specifically going to talk about energy conservation as it applies to mechanical energy. So mechanical energy is energy associated with massive objects that are moving or could potentially be moving, have the ability to move. So energy associated with moving masses. So for instance, if you throw a baseball through the air, it has mass and it's moving and therefore has mechanical energy. Or even if I held a baseball above the ground, it has mechanical energy in the sense that it's got potential energy, right? The potential to do work. So those are all forms of mechanical energy. There are, as we've talked about, there are other sorts of energy. Heat energy would be an example. So there's a broader type of energy conservation, right? So if I kick a soccer ball and the soccer ball goes along the ground and comes to rest, you might be tempted to say, that violates energy conservation. But it doesn't. It just turns out that the mechanical energy was converted to another type of energy, thermal or heat energy. So the energy is still conserved. It's just no longer mechanical. So basically, I've sort of gotten ahead of myself a little bit here, but energy conservation, to conserve means not to lose. So what this means is the total amount of energy is constant. So total amount of energy is constant. And since we're talking about mechanical energy, what we could say here is we could say that the potential energy plus the kinetic energy at some point, we'll call that 1, is equal to the potential energy plus the kinetic energy at some secondary point, right? That's one way you could express it. The total mechanical energy at a certain point has to be equal to the total mechanical energy at some later point. And so this is, for our purposes, this is what we're going to think of as the principle of mechanical energy conservation. The sum of the mechanical energy at one point equals the sum of the mechanical energy at another point. And maybe this is obvious, but it might be worth just mentioning the caveat that this only applies for conservative forces. So this is for conservative forces. So as I had just mentioned when I got ahead of myself, if there were some friction, this wouldn't be true, right? The amount of mechanical energy would change if there's friction, right? The friction, the energy dissipation of friction where this mechanical energy is lost as heat would violate this principle. So this only applies to conservative forces. So again, we're thinking about gravity or elastic forces, spring forces. Those are examples of conservative forces where this principle holds. And so bear in mind what that means is if we take a look at this equation here, if we think about this equation, this guy right here, this could be gravitational potential energy or it could be elastic potential energy, right? It could be either one of those. Also, obviously, this over here, this could be gravitational or elastic. Maybe the easiest way to think about this is to just kind of do a couple of examples. So I'll do an example here that just deals with gravity. So let's imagine I've got this is kind of a classic example, I've got a pendulum here. Try that again. So here's the pendulum, and I bring the pendulum so it's up some distance above the equilibrium point, right? So here's this mass on the end of my rope, right? And so the equilibrium point would be this low point down here, right? This is the low point. And what's happened here is that the pendulum has been raised some height. We can call that delta y in this case, some height delta y above the equilibrium position. And maybe we'll just, we call that 1.5 meters. Okay, and let's imagine that I bring it up here and I hold it at this point, so it's not moving. So the velocity here is 0, so it's not moving. So what we could say here is the total energy at this point is potential energy plus kinetic energy. Okay, what's the potential energy? Well, that's going to be mg. Let's give this thing a mass. Let's say that this mass is, I don't know what makes sense for a mass in this case. Actually, let's not even give it a mass. All right, let's not even give it a mass. Let's say that we don't know the mass of this object. It might be a little bit more interesting. And so now what I can say is potential energy plus kinetic energy. Well, at this point, the kinetic energy, it's not moving, right? So the kinetic energy is 0 at this point. And so this is simply mgh. I don't know m. I know that the height, the delta y, maybe I should call that mg delta y instead of mgh. I know the delta y, right, 1.5. I know g, but I don't know m. So I can't really calculate this directly. But maybe what I'm interested in is, maybe the question I'm going to ask is, what's the velocity down here? Right, when it gets to the very, very bottom of the arc, this equilibrium position. What's the velocity going to be there? Well, let's take a look. Down here it has, we could say potential energy plus kinetic energy. Well, what is the potential energy plus the kinetic energy here? Well, since it's at the bottom of the arc, I think it makes sense to maybe we'll call this the point of 0 potential energy. So potential energy equals 0. I'm sort of switching between the notation of PE for potential energy and U for potential energy. They both mean potential energy. So if we call this the bottom point, we call that the point of potential energy is 0, which I think makes sense in this problem. This is 0, so the total energy at this point is kinetic, 1/2 mv squared. And provided that there is no dissipation, no loss of energy, that means this must be equal to this. And so I can say that mg delta y equals 1/2 mv squared. And I can see right now I wasn't given an m, but I can see the m's are going to go away, right? I lose an m. And so I can go ahead now and solve for v, and I can say v is going to be the square root of 2g delta y, which with the numbers I've given, what's that? This is the square root of 3 times 9.8. So what's that going to be, like 5.4-ish? 5.4 meters per second. Okay. So we can see here that the total amount of energy as this pendulum swung down, the total amount of energy stayed the same, but of course what happened was all of this potential energy, right? All of the energy initially was this potential energy right here. This was PE. And all of the energy down here at the very, very bottom, all of that potential energy is gone. There's no more potential energy, and it's entirely kinetic. So that's a sort of a quick classic example of energy conservation with a pendulum. Let's do another case that will involve, this is a case that will involve both gravitational potential energy and elastic potential energy. Let's imagine that I've got some spring on the ground here. Here's the ground. I've got some spring, and there's a mass. I've got some mass on the end of the spring, and let's just say that this thing here has a mass of, let's say it's 0.1 kilograms. And let's imagine that I have compressed this spring, so it has been compressed down from its equilibrium position. Let's imagine that its equilibrium position is up here, but it has been compressed down some distance, 0.3 meters. So let's say that this delta y here is 0.3 meters, and this is the compression. The compression of the spring away from its equilibrium position. And I don't know, let's give this spring a spring constant. Let's say that the spring constant K for this spring is 150 newtons per meter. That's the K value of the spring. And maybe what I'd like to know is, well, first of all, let's think about what would happen here if I compress this spring down, and what would happen if I were then to let go. What would this spring would push upward on the box, wouldn't it? There'd be this spring force up, which would cause the the box, this weight here, to come flying straight up in the air. It would go up in the air, and then at some point later on, it would be up in the air here, and it would stop. Right, so it would be up here, and it would be stopped. That'll be the box at some later point in time when you let go of it. And what's happened there? Well, as it goes up, it has a certain amount of potential energy down here, and as it goes up, that potential energy is diminishes, right? It decreases, and at the very, very top, that potential energy, what has happened to it? Well, initially, the potential energy here that's stored in the spring decreases, and it gets turned into kinetic energy. And then there's a certain point when the block is now, or the box here, is no longer in contact with the spring. And at that point, the box is going to be at its maximum velocity, right? That's when it's going to be moving at its fastest. And then beyond that point, it's going to go up. And as it goes up, that kinetic energy is going to decrease again. And as the kinetic energy decreases, it gets converted back into potential energy. So, maybe here's the block, maybe right here. Right, here's the box when I'm imagining that this is when the box is no longer in contact with the spring. So what we could say maybe here is initially at this point, right here, it is all elastic potential energy. And then at this point right here, when the spring is fully released, right, there's some amount of gravitational potential energy, right? It's above the low point. It's above the starting point right here. So there's some amount of gravitational potential energy, but there's a lot of kinetic energy as well. And then when it gets to the very, very top now, the kinetic energy is gone. Obviously, there's no elastic potential energy, so now it's all gravitational potential energy. So as the box goes up from here to here and then to here, the gravitational potential energy keeps getting bigger and bigger and bigger and bigger because it's getting higher and higher above this reference point. This is what we're calling the 0 point for potential energy, right? It's getting above and above and above, more and more and more gravitational potential energy. I should say this is my 0 point for gravitational potential energy. And then right here, as it gets to this point, this is the maximum kinetic energy, right? It speeds up, and now slows down, because there's now a downward force on it. Hopefully that makes sense. But what I'd like to figure out, what I'm going to ask, the question I'm going to ask is, what is this maximum height? So, what is this max height? That's what I'd like to know. What is this? And it seems like it should be pretty complicated because we've got elastic potential energy down here, and there's gravitational potential energy and kinetic. You'd have to do some sort of conversion and then convert it back to gravitational potential energy. But we can make this a little bit easier by recognizing the fact that all of this elastic potential energy will get converted into gravitational potential energy in the end. Assuming, again, there's no loss of energy due to heat, all of this will turn into that. So what I can say is 1/2, maybe I'll write it this way. The elastic potential energy at the starting point is equal to the gravitational potential energy at the end point. So this is the start and this is the end. And I'm sort of ignoring this middle section, right? Because presumably in the transfer here, there's no energy lost, so it all comes up to here. In other words, now I can say 1/2 k delta y squared, that's the elastic potential energy, equals gravitational energy, which is mgh. So I'm calling delta y is this distance right here, and h is this distance right here. Okay, so this is just our equation, right, for elastic potential energy, and this is our equation for gravitational potential energy. And what am I looking for? Well, I'm looking for h, so I can go ahead and just isolate h. So I'll write that over here. I'll say h is what? It's going to be k times delta y squared over 2 times mg. And I've got all these numbers, so I can say, now I'll continue down here, I'll say h is going to be 150 times 0.3 squared divided by 2 times 0.1 times 9.8. do that out and you should get something like 6.9 meters. Meaning, right, as the spring releases, it goes up this, it speeds up over this distance, 0.3 meters, and then slows down, and goes up an additional 6.6 meters, right, to get up to 6.9 meters. So this distance right here is 0.3, and this distance right here would be 6.6 meters above. So the total height from the release point is 6.9 meters. Okay, hopefully those examples help to illustrate this concept. We'll be practicing it more next class.